just to wait and then hand it off to you. Okay, good afternoon, everybody, and thank you for coming to the afternoon session of the ADA's invited talks. We have two excellent speakers lined up for you. And as a quick reminder, the ADA's invited track happens every day for the rest of the conference, so Wednesday and Thursday at 10 o'clock and then at 1:30 as well. So with that, let me introduce our first speaker for the afternoon, Dr. Naila Murray. She obtained a BSc in Electrical Engineering from Princeton University in 2007, and in 2012, she received her PhD from the University in Barcelona in affiliation with the Computer Vision Center. She joined Xerox Research Center Europe in 2013 as a research scientist in the computer vision team, working on topics including fine-grained visual categorization, image retrieval, and visual attention. From 2015 to 2019, she led the computer vision team at Xerox Research Center Europe and continued to serve in this role after its acquisition and transition to becoming Naval Labs in Europe. In 2019, she was the director of science at Naval Labs, and in 2020, she joined Facebook AI Research, where she is the senior research engineering manager for EMEA. She has served as an area chair for ICLR 2018, ICCV 2019, ICLR 2019, CVPR 2020, and ECCV 2020, and a program chair for ICLR 2021. Her current research interests include few-shot learning and domain adaptation. And today she's going to be talking to us about training deep vision models in low data regimes. Please give a warm welcome to Naila Murray.
Good afternoon, everyone. Thanks so much, Suju, for the introduction, and thanks to the organizers. It's a pleasure to be here. So as Suju mentioned, today I'm going to be talking to you about some recent works on training vision models and deep vision models in particular in low data regimes. So to explain a bit what I'm going to talk about, let's take a look from sort of the other end of the spectrum, which is machine learning in the high data regime. So this is, I think, a pretty well-known paradigm with a very successful history of leveraging large-scale data sets. So for folks who are familiar with the vision domain or even the natural language domain, there's a pretty compelling history of using Imagenet data sets such as Imagenet, which is a large-scale annotated and human annotated data set, and using this to create very powerful, very discriminative representations for visual content, right? And typically, it's used in order to pre-train such models. So for example, large convolutional neural nets, or maybe more recently, visual transformers. And they're pre-trained on this data set using different sort of techniques. So you can imagine a supervised setting, or weakly supervised setting, or even, very popular these days, self-supervised approaches. Also in text, in the past few years, this has become extremely successful as well, using similar techniques to train models to represent language. And what do we do once we have these very powerful models that are trained to very well represent certain types of modalities of data? You can use them to fine-tune, right? So you can fine-tune them on downstream applications. Because of course, you're not interested in having a discriminative representation just for the sake of it. You're interested in having this in order to perform some sort of downstream task, right? Some target task. So let's imagine you have this task of let's imagine you have AR glasses and you want to be able to recognize objects from some sort of egocentric point of view, like for example, this white cup. You would like to be able to train a model to do that, and so then what you would do is you would take this model that has been pre-trained, that gives you good visual representations, and then you will adapt to this actual task, right? And another potential application could be for driving assistance, where you would like to be able to detect, for example, vehicles in some urban scene. So this paradigm assumes that you have large-scale data for pre-training, and then also some amount of supervised data, a fair amount of supervised data, also for fine-tuning your final task. But you can imagine that there are many downstream applications where it's hard to collect the amounts of data you need even for your downstream tasks, right? And especially, it's hard to collect large amounts of supervised data, for example, like using human annotations. So to give an example of this, I think one that's pretty intuitive. So let's imagine you have a user query, and your task is to match this user query. Here you have a visual query of an image, and you'd like to match it to some online catalog. Let's say you have a user who would like to say, I've seen this object and I'd like to find it because maybe I want to purchase it. So you would like to be able to sort of match this query to a database and then retrieve something similar that the user might want to purchase. You can imagine that this is a very dynamic task where you have catalogs that are coming online and offline very quickly, and you would like to be able to adapt your matching model to new data that's coming online. Being able to collect data on the fly and in a continuous manner using human annotations to retrain your model is not really practical. Another example you can think of is from online forums, online communities, where you might want to moderate user content. And you can imagine that there's new types of content coming online very often. You might have new policies, content moderation policies, for example, that you would like to apply, right, in some automated fashion. And you would want to be able to continuously apply these models and adapt these models to new contexts, new policies, without needing to retrain your model, at least not on a large amount of data, right? And once again here, the paradigm of fine-tuning your model using supervised data is not really applicable. So what I'm going to discuss in this work is an alternative to this approach, this paradigm of pre-training and fine-tuning on large amounts of supervised data by using instead weakly supervised model adaptation to new and out-of-distribution data. So I'm just going to take you on a tour of 3 recent works that apply this, this sort of alternative paradigm of using small amounts of data in a weakly supervised fashion. And I'm going to start with one example, which is in, as I mentioned, the visual domain, and this is the topic of action segmentation. So for those of you who are unaware, action segmentation is the following task. So you're given a video, right, so a sequence of frames, and you would like simply to temporally segment that video. So let's imagine you have some activity that's being performed. In this case, this is the activity of making coffee. And so you can segment that activity into certain sub-actions, right? So this could be lifting up the cup, spooning in powder, and so forth. And so you can think of this fundamentally as a grouping problem where you're trying simply to group frames of this video. So given this, if we approach it from this point of view, we can think of this, we can adopt a clustering approach. And the key inductive bias we use in this work is to assume that the cluster should be not simply visually coherent, but also temporally coherent as well. And this is a fairly simple and maybe somewhat simplistic assumption, but you'll see that it's actually fairly powerful and it gets us a long way. So to go towards the visual temporal frame clustering approach that I mentioned, I'll just describe to you a little bit how we start this off, right? So first of all, we're starting off with a graph, and when we have the graph, we'll do clustering on the graph. So let me just describe a little bit how we compute this graph. So we're assuming we have this video, right, with n frames for this specific video, and not every video will have necessarily the same amount of frames, of course, so this is a per video number. And so for each of these frames, we have some visual representation, like some vectorial representation, for example, xi. And for this, we're going to just define a directive graph between frames, right? So vertices are frames, and the edges will encode some distance between those frames. In this case, we're going to encode these edges as a combination of separate graphs, one graph which represents appearance distance or visual distance, and another which will be temporal distance. So the description of the edges, the computation of the edges that are based on visual distance is the equation you see on the left. So this is simply, so before I mention, I'll just say that each visual representation xi is L2 normalized, so that this is going to be a maximum of 1 and a minimum of 0, right? So this is simply saying it's a simple cosine similarity between different frames, right, using visual representations. And then on the temporal side, we simply have, once again, a simple difference between frames, between timestamps of frames, normalized by the length of the video. And then once we have these two sort of separate notions of distance, we combine them with a simple product, and this gives you our edges. And then once we have that, we compute our final graph by taking this and computing a binary affinity matrix, you could say, between all frames, okay? So what we're going to do is we're going to say if we have a frame I and a frame j, the distance, or let's say the distance between those will be 0 if frame j is the closest to frame I from a visual temporal perspective, and it'll be 1 otherwise. So in this sense, we have one nearest neighbor graph. So once we have this graph, what do? We can do a variety of different clustering approaches. In our case, we use a hierarchical clustering method, which is going to start off with an over-clustered and over-segmented set of frames, and we're going to continuously agglomeratively cluster them until we have one large cluster. I won't go into the algorithm, but I'll simply say that this algorithm gives us a set of clusters, each of them being organized in a hierarchical fashion. And so what we have is this as input is the number of clusters that we expect. And so this is sort of like the one input we have into the algorithm, the number of clusters k, and then we simply look in this hierarchy for the hierarchy with the closest match, and this is what we choose. So you'll notice here that so far I haven't mentioned labels at all. So we're simply assuming that we have some notion, some way to represent our frames, and once we have that, we proceed with this clustering technique. So how do I evaluate it? I won't go into a ton of detail here. I don't think it's really the most important thing, but I'll simply say that we use some data sets that are based for action segmentation. And in terms of the evaluation, once again, we're not assuming we have any labels, right? So we have these clusters, but they don't have any labels. They have just pseudo-labels, so cluster assignments. So you might want to ask, how can I actually evaluate the accuracy of this, right? Like how good the clustering is. So what we do is we took a pretty standard evaluation technique, which is where we apply a Hungarian matching between our pseudo labels and the labels we have, the ground truth labels we have of the clusters. And this gives us some notion of how good our clustering is. And for metrics, we use accuracy, and we also use intersection over union between our clusters and the ground truth clusters. So I think in terms of comparisons, what I think is interesting is to think about some of the baselines we used here. So we used, to start off with, a very, very simple baseline, which is simply taking our frames, our video sequence, and dividing them equally into equal sections, right? So this is extremely naive. The surprising thing is this actually works very well. It works online with quite a few recent unsupervised methods. So this just tells you that there's quite a lot of bias in these data sets just to begin with, right? Another fairly simplistic baseline is simply to look at to simply attack this from a vision-based perspective, right? So to discard notions of temporal contiguity and to simply cluster the visual features, right? And if we do that, we also get a pretty good result as well. And then we also use a slightly more complex clustering method, which is a hierarchical clustering method, which also did quite well. So what we see here is that these baselines, which you can think of as temporal clustering baselines and visual clustering baselines, already quite strong baselines compared to recent work. And then what we saw is that with our work, which sort of combines these two into like a visual and temporal clustering, this gives us a pretty strong boost in performance. And you say, yeah, I'll simply say here that this also compares quite well to state-of-the-art works. So what did we learn from this work? We saw that a clustering approach here without using any labels performs quite well on a task that on the face of it may seem somewhat complex. We saw that appearance-based clustering baselines are quite competitive, and as I mentioned, there's no training required on any training videos to produce these coherent segments. Of course, there's some limitations to this work. The first one would be that it's quite possible to over-segment your clusters using this fashion. And also, as I mentioned earlier, we're assuming temporal contiguity, which is not going to hold in all cases. So there are some limitations here. So moving on to another type of work, like in this general area. So this is a topic of, the task, I should say, of few-shot object detection. So let me explain a bit what that is. So in this case, what we'd like to do is to perform an object detection task using very few samples, right? So what is object detection? For those of you who may not be super familiar with it, you're given some input image, and you'd like to run it through some sort of network that can output some objects of interest within the image. So in this case, for example, we're interested in knowing whether or not there are any dogs on this image, and what you would like is that the network would output you the location, for example, indicated with the bounding box, and also the class of the object within the bounding box. So that's the problem of object detection. And what do we mean by few shot is that we would like to train a model for this task using as few shots or as few examples as possible. So typically, we're interested in cases where we have on the order of 1 to 10 examples per class. So a common paradigm for this work is to, as I mentioned from the beginning, adapt a pre-trained model with a set of episodes. And these episodes consist of a query image, so for example, an image you see here, some support images, so these are the shots, right? These are the examples of the class of interest. And you're going to have some set of support regions for every class, right? So if you have an L-way episode, you'll have L different classes that you want to categorize in between. And so once you have these episodes, you're going to use some encoding network here to output some feature representations of both the query, of both the support and the query image. And then you're going to, once you have these two sets of representations, you're going to compute some similarity between those to give you the output predictions that you're interested in. So as you can imagine, the notion of similarity here is quite important, right? Because we have so few examples, we're only going to be able to tackle this task by relying very much on the similarity between the query image that we have and the examples that we have as well. So what are some ways to compute similarities between these features? I think a very straightforward one you can imagine is computing simply the inner product between the vectorial representations I showed before. That's quite simplistic, but it has a great benefit of the fact that there are no new model parameters, which is really key in this setting where we have on the order of 10 or 20 or 30 examples to train from, right? So in this setting, you really don't want to introduce a large number of parameters. On the other hand, of course, you're going to be left with a similarity metric that's somewhat simplistic, right? It's not going to be able to enhance the expressivity of your representations. If you took it the other way around, you sort of have the opposite effect, right? If you, for example, input it, you sort of introduce some new sets of features, like a layer of, for example, multi-layer perception with a nonlinearity. This, on the other hand, would give you potentially an expressive similarity metric. At least you'd be able to have a very expressive function. On the other hand, you're introducing many new model parameters. That's probably not going to be very practical. So one sort of way to get the best of both worlds in some sense is to, for example, consider kernelized linear inner products between features. So this allows you to have a similarity metric that's somewhat more expressive, right, than a simple linear inner product, while introducing pretty much no new parameters, so almost no parameters. So that's the approach we take by using nonlinear kernels. In particular, we use standard kernels such as the RBF kernel, which allows us to control smoothness of our decision functions, and then also polynomial kernels as well. So here's the full pipeline for our work, which we call a kernelized few-shot object detection work. In this case, as I mentioned before, it follows very much the sort of pipeline, the paradigm I was describing initially, where here we have an encoding network, and then we have this kernelization block, which allows us to compute, given some set of feature representations, to compute some more expressive features based on the kernelization approach I'm going to describe. And once we have these, we're going to compute similarities between these more expressive features in order to produce our predictions. So the encoding network, it's relatively straightforward. It's not really the focus of our work. I'll simply say that we're using features extracted from a standard convolutional network, in this case ResNet. And then for the number of support regions that we have, so the number of shots or examples that we have, we're going to simply average over them to give us some representation of the class of interest. And we're going to extract multi-resolution features to give us these output features. So once we have this encoding network, this gives us a set of features phi for our support regions and a set of features phi star for our query. And next, once we have these, we input this into the kernelization block. And so here we have the key part of this block, I would say, for the purposes of this talk, is the kernelized autocorrelation unit. So this unit, it takes as input the features phi, the feature matrix phi. I think this is dying a little bit. So you'll have to try to follow along with me. So we take along this feature matrix phi, and we are going to compute our KHS kernels and kernelized autocorrelation matrices K, right? So, and we compute them using the equations you see below. So you see there's kind of two flavors of the same computation. So this is going to give us a matrix of size k by k, or I should say d by d, where d is the number of features. And each element, each entry in this matrix is going to be computed as you see there. A relatively simplistic computation, but where we introduce the expressivity is with the nonlinearities that you see. So the nonlinearities is the function rho, which can be either, as I mentioned, a polynomial kernel or an RBF kernel, for example. So what this is going to give us is it's going to give us, for an input data matrix phi, it's going to give us two flavors of both a polynomial kernel and RBF kernel. So in the end, we're going to get 5 different matrices for every input matrix that we have. So this is great. This means that because normally in our setting, n is much smaller than d, we're sort of lifting our representation into a higher dimensional space and a more expressive space, representational space, which is great. But of course, on the other hand, I'm sure many of you are thinking this is probably going to be a bit expensive, right? Because you're going to have a larger feature space at the end. So what we've done to sort of mitigate that is to perform some pooling using this approach here. So what this is a sort of diagonalization approach, which takes our input matrix representation, like one of the 5 I just described to you. It computes a sort of featured decorrelation, you can put it, where we sort of diagonalize to some extent all the information in the matrix, and then we extract the diagonal from that. So what that means is that for every feature matrix that we have just created, right, each kernelized representation, we're going to diagonalize that to some extent, which will be controlled by this eta factor here, and then we're going to extract the diagonal from that. So that means that we're left back with a d-dimensional representation. So this gives us a good trade-off between having more expressivity without introducing increased computational complexity. Yes, and that's learned using a very small MLP. So for some experiments here, we compared with standard experiments in the literature, standard data sets in the literature, and we used different versions of average precision to evaluate the work. And we saw that this does compare quite favorably with state-of-the-art methods. I think what's interesting to look at into a bit more detail is the effects of these kernels. So what we looked at is different choices of kernels, for example, sticking with a linear kernel, which is you consider some sort of baseline, or using different flavors of the RBF kernel, different versions of the polynomial kernel. In our case, we use a quadratic kernel, or different combinations of them. And what we did see is that, as you might probably guess, RBF kernel performs quite well. However, what was interesting for us is that we saw that combinations of that, of all of them, did give us the maximum performance that we saw. So that's the end of that piece of work. I'm going to talk through a little bit now a pretty related work which takes this idea and pushes it a little bit further. So in the previous work I just described, we saw that we can use these kernelized representations to increase the discriminativeness of the representations we're using. And then we can also, post hoc, use some sort of second-order pooling to reduce the dimensionality of those features while still maintaining increased discriminativeness. So in this work, we're going to take this up a bit of a notch by using even higher order descriptors, which we call higher order tensor descriptors, which will be using only polynomial kernels, but we'll be using polynomial kernels of higher order than 2. And we'll see that this also is quite effective. So the full pipeline is similar to what you see here. I think the key difference I would highlight will be in what we call the tenet module, so I'll spend a bit of time there. So here, to dive into this a little bit, let's assume that we have, I'm just going to describe a little bit the kernel we're going to use here, right? So let's say that we have 2 sets of features, 2 sets of, you can say, feature matrices, right, phi and phi prime, both with potentially different numbers of features, n and m. You can compute a kernel between these as a linearized sum of kernels, showed by the double summation you see there, right? So you can see the kernel within the summation, right? So you have this inner product to some order, R, and that indicates the order of the polynomial. And this can yield a feature map, right, which is what you see below. So in this case, what this simply is for a given set of features, you take every feature, you compute the outer product of that feature to some order. Okay, so this order could be 2, 3, or 4, which would be like, for example, for 2 would be a quadratic kernel. polynomial kernel. And then you simply take that outer product, you compute it for each feature, and then you sum over that, right? So this gives you a very high order, very expressive representation. Because what you're going to get at the end of that is you're going to get a feature, a tensor of dimensionality r to the power of d to the power of r, where r is your order, okay? So this, once again, you can see that we have this input representation, and rather than use something like an MLP, which has a lot of parameters, we're simply going to use this kernelization approach to give us a very expressive representation without introducing any significant number of parameters. But of course, once again, we have the same question, right? We started off with a set of features of size, for example, d by n, and now we have a set of features. We have a feature tensor of size d to the power of r, right? So for a large r, that can be quite big. And so we adopt the same approach that we had before, where we diagonalize this tensor in an identical analogous approach, and then we extract the diagonal of that, using, once again, this eta factor to adjust the amount of decorrelation we can achieve. And here, once again, we adopt a similar evaluation paradigm, and we did see that our results compare quite favorably with existing approaches. And then once again, we did a bit of ablative analysis to consider what orders of polynomials can we use. And we did find that using r equals 2 is most effective if we had to choose between one of them. However, if we were able to make some combination of those, we do see that it is best to combine different versions of the kernel. So to combine representations of order r equals 2, 3, and 4 in order to get a maximum performance. So to conclude here, we saw that both the last works I mentioned, the kernelized FSOT and this version, use inductive biases to generate these highly discriminative representations. And we saw that in both cases, we were able to increase the discriminativeness of the representations that we were using to compute similarities between support and query regions without introducing a significant number of model parameters. And so that's it for this talk. I'd just like to quickly thank my collaborators, and I'm happy to take any questions. I really think it boils down to the amount of data you might have access to at this stage of the process. It's hard for me to think of a case where you could go with an MLP. Maybe if you're extremely constrained in terms of computation, because there may be a trade-off you can make where, on the one hand, you might have limited data and therefore you can't introduce a lot of new parameters, but on the other hand, this can be a bit expensive in terms of the dimensionality, right? So I was able to, we were able to, in this work, reduce the dimensionality a fair bit, but it still is higher dimensional, right? So you might decide that you'd want to keep the dimensionality of your actual representation, even if the computation to get you there is a bit expensive, and that might be worth it, even if the features that you would use in that case would be some MLP that's not, maybe not as well trained as it could be. So there might be some scenario where that works.
So what is the real trade-off when you diagonalize? Are you missing out information that you can later measure and say, okay, this diagonalization was working great for these set of data, doesn't work so well? How should you think about that problem?
No, that's a great question. So the diagonalization, you can think of it, I mean, it's quite intuitive when you look at the equation that you see that you can consider it a kind of shrinkage operator between the identity matrix and let's say your kind of feature representation, right? So you have this notion of an identity matrix where you have a completely decorrelated but also completely uninformative representation, and then you have this full matrix which is is informative, but at the same time, it's the information is not really concentrated, right? So you kind of have to spread it over like a lot of parameters. So the trade-off that this ETA is making is it's saying we're going to try to shrink this, right? So kind of decorrelate your matrix so that it approaches an identity matrix in its form, while not completely losing all the information in it. So what you're going to get is some trade-off between how diagonalized and how concentrated the information is on that diagonal versus, I should say, how kind of large your representation is. So because you can only do one or the other. You can only have a diagonalized representation, or you can have this large feature matrix. And the problem with having this feature matrix is what I mentioned, right? If you have a feature matrix that's d to the order of 3, right, which is maybe 1,024 times 3, to compute a similarity between that, it's going to be, it may be that, that the follow-on network, right, for example, the relation network that follows on from this network is not able to, like the dimensionality is too high for it to be able to extract like a reasonable and a useful similarity. So you kind of have to reduce your dimensionality, and this is why you kind of have to choose between one or the other. So eta is going to be, if eta, for example, is too, if it's too low, then your diagonal is going to, it's not going to contain as much information. It's not going to be shrunk. This shrinkage operation is not going to be very effective, right? And if eta is high, then you decorrelate a fair bit, but then the decorrelation actually destroys information to some extent. So that's what you kind of have to trade off between with the two, yeah. And we did that with and as I mentioned, an MLP, which kind of predicts the best data. Yeah. We did get state-of-the-art results. I don't remember exactly the margin of kind of improved performance, but we did improve on, at least on the average overall classes. I believe, yes, it is. I can point you to it. I don't think I have it here, but I'm happy to point it to you offline.